Hello! In this video we will talk about reduction-oxidation reactions, or better known as redox reactions. Now, redox reactions are really important because, for example, they're the source of all the electricity that you use in any mobile device, any battery, anything like that. It all comes ultimately from a redox reaction. So there's a ton of applications here. So at its core, a redox reaction is one where electrons are transferred between species. It's really that simple. So if you look on the left here, the sodium and the sulfur, they have no charge. They're pure elemental state, perfect. And then if you combine them to make sodium sulfide, the ionic compound, well, in this compound, each sodium is a +1, each sulfide is a -2. So in the process of this reaction, electrons were transferred from one to the other. So we have this sodium here with this electron hanging out, and it goes over to the sulfur in order to make this reaction happen. And then this happens twice because there's two sodiums, so you get two electrons onto the sulfur. Now you're left with two sodium ions, and then a sulfur that has its octet, its -2 charge, and everybody's happy. And then now the sodium is positive, the sulfur is negative, and they stick together through electrostatic attractions. This is our basic idea of how an ionic compound is formed, and what we didn't tell you at the time when we were discussing these earlier is that this is a redox reaction. So there's some words that go along with this that describe what's happening, and we need to know these words because it's important for a lot of chemistry, so I want you to know them. And here's some ways to remember them. So, alright, sodium loses electrons, and that process is called oxidized. This phrase originally meant it makes more bonds to oxygen, so that made sense. But we've broadened the term as collectively we have learned more about chemistry, and so now oxidized means it loses electrons. On the flip side, sulfur gains electrons, and that's reduced, because the charge of the sulfur is numerically reduced, so that makes sense. In my head, I keep these straight because I can remember that reduced means that the charge goes down, and then oxidation is the other one, the charge goes up. There's some mnemonics you can use. The one that I typically recommend is oil rig. Oxidation is loss of electrons, and reduction is gain of electrons. And so I think that works pretty well. So you can use the mnemonic if you like. Again, I just remember what's reduced, that means the charge goes down, and I can usually figure it out from that. Now, some more complicated words here. Sodium, it loses electrons. Also, by reacting with sodium, the other stuff is reduced. So sodium is the reducing agent. It's the one that makes the reduction happen, like the agent of change makes change happen, things like that. So the sodium in this case is the reducing agent. It's also called the electron donor sometimes because it gives the electrons away. And the reducing agent itself is oxidized. Sulfur, on the other hand, it is the oxidizing agent because it makes the oxidation happen by reacting with sodium. And so the oxidizing agent is itself reduced, but it's the one that makes the oxidation happen. So really, I think the tricky thing here is keeping all the words straight. So let's give an example. So here's a reaction. Which one's oxidized, which one's reduced, which one's the oxidizing agent, which one's the reducing agent. In doing a problem like this, I think it's a great idea to start by writing the charges next to or above each element. So zinc, just by itself, is no charge. It's its elemental state. Well, sulfate, SO4, is a -2, and we know that because we've dutifully memorized our polyatomic ions. And so that means copper, in this case, has to be a +2. Alright, so over here, the zinc is a +2 for the same reason, because the sulfate is still -2, and then the copper is now 0. So if we track this out, the zinc atoms went from 0 to +2, and so that charge went up. The copper atoms went from +2 to 0, so that went down. So the way I do it is I say the copper was reduced because its charge went down, so that's the species that was reduced. The zinc is the other one, so that's the species that was oxidized. Or if you want to think about oil rig, oxidation is loss of electrons. For zinc to go from 0 to +2, it had to lose the negative electrons, so that means it was oxidized. Reduction is gain of electrons. For copper to go from the +2 to the 0, it had to gain electrons. Alright. Now zinc is oxidized, so that means it's the one that made the reduction happen. So zinc goes over here. And then copper is reduced, it's the one that made the oxidization happen. And so it's the oxidizing agent. So if anything, the species that's reduced, the oxidizing agent, just switch the words for the same chemical, right? Copper's reduced, it's the oxidizing agent. Zinc is oxidized, it's the reducing agent. Now something else to think about is how many electrons are transferred in this reaction. I introduced this concept here because it's important for you to know how to do it when we revisit this kind of material in the second semester of general chemistry. So, how many electrons are transferred here? Well, zinc goes from 0 to +2, so it has to shed 2 electrons to make that happen. Copper goes from +2 to 0, so it has to gain 2 electrons to make that happen. So there are 2 electrons transferred in this reaction. Okay, so now here's a much harder example, so let's work through this. The first thing to do is to go through the various pieces in this reaction and figure out what the charges on each part are. And a number of these are pretty straightforward. Look, the uranium, that's +4 because it says +4 right here. Okay, that's easy. The cerium here is +4 because it says +4. Alright. Now, water, I think it's illustrative to think of water sometimes like it's an ionic compound. And so in this case, the oxygen's -2, and each hydrogen is +1 in order to make that work as an ionic compound. Okay, those charges will neutralize out. Great. Now, the uranium oxide ion here, this one's a little trickier to figure out the charges involved. So we don't know what uranium is because it can take multiple charges. The oxygen, we know that oxygen's going to be -2, and then there's 2 of these oxygens here. We don't know what the uranium is, but we do know that this overall will add to +2 because the charge on this whole ion is +2. So now we're just solving for x. Whatever x is, that you can then add to 2 times -2 for the oxygen, and then this equals a total of +2. So if you solve for x, you get 6, +6, -4 equals +2. So in this case, the uranium is +6, and the oxygen's -2. Great. Over here, the cerium is now +3, and then the hydrogen's +1. All right. So we've done the hard part. Now we just look at this and try to figure out which species changed. So I can see that the cerium goes from +4 to +3. And so that means the cerium was reduced because this charge numerically went from a higher number to a lower number. It was reduced. All right. The uranium, on the other hand, went from +4 to +6. So it had to lose electrons to make that happen. Oxidation is lost. So the uranium was oxidized. Now let's look back up at the question. What are we trying to answer? The species that are oxidized and reduced, and the number of electrons transferred. All right, so if we look at this, there's a single uranium atom here, and each single uranium atom has to lose 2 electrons to go from +4 to +6. Now, what about the cerium? Each cerium atom goes from +4 to +3, which means it has to gain 1 electron, but there's 2 cerium atoms. So that means the cerium overall gains 2 electrons. So that means 2 electrons are transferred because the uranium is overall losing 2, the cerium overall is gaining 2. Perfect. And while the problem doesn't ask for it, let's be complete here. And since cerium is reduced, that means cerium is the oxidizing agent. And the uranium is oxidized, which means it's the reducing agent. All right, and that's how you work with a reduction-oxidation reaction. And that's all we have for this video. So take the time to learn the vocabulary here and how to identify which parts are oxidized and reduced. And that's all we're going to learn for now. but it is important that you learn it because it comes back in the second semester of general chemistry when you have to do a lot more work with it. So it's good to learn now. All right, thanks for watching.